Let's look at the naive Bayes technique for classification. Now, this technique is based completely on concepts of probability, and it might be a good idea for us to review some concepts of probability right now. While reviewing probability, I don't intend on going too deep into the basic concepts of probability, like getting into probability distributions and all of that, but I do want you to get a good grasp for what is probability and how it's applicable. Because time and again in data analytics, probability does show up. And it's useful for you to have a good grasp of probability. Let us say that we have a set of people represented inside this rectangle. And you can see that some of the people, each circle or each oval represents a person. And you can see from this that some of them are solidly shaded and some of them are not. Let's say, for argument's sake, that the solidly shaded ovals represent customers of our company and the others represent people who are not customers of the company. Of course, the total number of people is the number of ovals inside this box. So clearly, if you count up, you can see that there are 5 buyers represented by the 5 filled ovals. And let's say that the others are non-buyers, and that happens to be 8 non-buyers. Once again, we can count and see that that is the case. So there's a total of 13 people, of whom 5 are buyers. Okay. Now, suppose we consider a scenario where we randomly pick one person from this set of 13 people. Okay. So what is the probability of this randomly chosen person being a buyer of our company's product? So clearly, since there are 5 buyers and a total of 13 people, if we repeat this experiment often enough, you'll see that roughly 5 by 13 times, that is the proportion of, with the proportion of 5 on 13, you'll see that the person you randomly choose is a buyer. And by a proportion of 8 over 13, you will see that this randomly chosen buyer person is a non-buyer. Okay, this is like tossing a coin. If you toss a coin a large number of times, then you expect to see that roughly 50% of the time it comes up heads and roughly 50% of the time it comes up tails. Okay, so this is a notion of probability seen as a relative frequency. And for our purposes, that view is sufficient. Now, in probability theory, there is another view of probability. We're not going to get into that. Okay, so we're going to look at this view as a relative frequency. Okay, so if you do it often enough, what's the proportion of this event versus that event? It's as simple as that, very straightforward concept. Okay, so in general, probability of an event is the number of favorable outcomes, that is, number of outcomes that signify the occurrence of the event, divided by the total number of possible outcomes. Okay, so if you pick 13, if you pick people randomly from this set many times, okay, so you might say, let's say you did this experiment 100 times, then roughly 5 by 13 times 100, that proportion of times it will turn out to be a buyer, and the rest of the time it will turn out to be a non-buyer. Okay, so the probability of an event is the number of outcomes that signify the event divided by the total number of possible outcomes. Okay, so here we've got another slightly larger set, which consists of 36 people, out of which 12 happen to be buyers, and therefore the probability in this case would be 1/3 or 12 divided by 36, which is 0.33. Okay, so here you've got, let's say, 3 classes instead of 2 classes. Okay, so you've got a total of 16 people. I've added 3 people who are here, who are, let's say, undecided. Okay, so we can say probability of buyer is 5 by 16, non-buyer is 8 by 16, which is a half, and probability of a person who you pick happens to be undecided is 3 by 16. And of course, if you consider the sum total of all possible events and add up their probabilities, it'll come up to 1. Okay, assuming that these are mutually exclusive. Okay, so for example, here, if you consider the probability of a randomly chosen person being a buyer and an undecided person, that is obviously 0, right? Because if a person is 1, according to our scenario, the person cannot also be the other, right? So if a person is a buyer, then the person is a buyer. The person cannot be a non-buyer. If a person is undecided, then they cannot be a non-buyer or a buyer or whatever, right? So in that sense, all of these events we are talking about, the buyer, non-buyer, undecided, these are mutually exclusive events, right? If one occurs, then the other cannot occur in this scenario, okay? So therefore, the probability that somebody can belong to one and the other when both are mutually exclusive, that probability is zero. It's impossible to occur, okay? On the other hand, if you pick people randomly from this, the probability that the person you picked is either a buyer or is undecided is the sum total of those two probabilities, namely half. Okay, buyer and undecided. 5 plus 3, 8 divided by 16, that's half. Okay, so in other words, when you've got mutually exclusive events, the probability of one or the other occurring is simply the sum of the two probabilities. Probability of buyer or undecided is probability of buyer plus probability of undecided, provided the two events are mutually exclusive, right? So for mutually exclusive events, probability of A and B, where A and B are events, is 0, and probability of A or B is probability of A plus probability of B. Okay, so that is with respect to mutually exclusive events. So when two events are mutually exclusive, then the occurrence of one means the other cannot occur. That is, the occurrence of one excludes the occurrence of the other. On the other hand, there is another concept of independent events, okay, which is different from mutually exclusive events. With independent events, both events can happen simultaneously, and the occurrence of one does not affect the probability of the occurrence of the other in practice. Okay, I say in practice because, of course, we're all fond of saying that in the real world, everything depends on everything else. Okay, so really at a completely theoretical level, there cannot be any independent events because everything in the world affects everything else. But in practice, several things are independent. So for example, one event may be the event that I get a speeding ticket while driving to work, let's say today or any particular day. And the other event is that on the same day, it rains in Seattle. Okay, so the two things can happen simultaneously. I could be getting a ticket while it's raining in Seattle, or the other way, I could be getting a ticket and it's not raining in Seattle, or it's not raining in Seattle and I'm either getting a ticket, not getting it. Both of these are completely independent in practice. But of course, in theory, you can say, well, when you drive the car, there's some, you affect the wind and finally that could have an effect somewhere else. Yes, all of that is true in theory, but in practice, these two are independent events. They're not mutually exclusive at all. They are independent. Both can occur simultaneously. And the point is that the occurrence or non-occurrence of one event has no effect on the occurrence or non-occurrence of the other event. So that means these two events are independent. Okay. A more traditional example is, suppose you toss a coin. The probability of getting a head on this coin toss is completely different or completely independent of you, let's say you roll a die and the probability of getting a 2 on a die roll. That is, you toss a coin, you roll the die, there are many possibilities and all of them can occur. The coin toss has no impact on the die, or the die roll has no impact on the coin toss. These are independent events. Okay, the occurrence of one does not affect the probability of the occurrence of the other. So if you look at getting a head on a coin toss, the probability of that is half. We know that, assuming the coin is fair. And the probability of rolling a 2 on a single die roll is 1/6. Once again, assuming that the die is fair. It's not loaded in any way. Okay. And when you have independent events, the probability of both of those events occurring, A and B, is probability of A times probability of B. You multiply. Okay, when they are independent. Okay, of course, we already saw that when two events are mutually exclusive, the probability of A and B occurring is 0 because they are mutually exclusive. One will exclude the occurrence of the other, right? Whereas if they are independent, then you just multiply the probabilities. Okay, why do you multiply them? It's quite easy. You can see this if you can, if you look at these two events of tossing a coin and rolling a die, okay, what are all the possible outcomes? Well, the coin could turn up head or tail, and the die could turn up 1 or 6, 1 through 6. Okay, so these are the 12 possible outcomes. Okay, these are the 12 possible outcomes for a coin toss and a die roll done one after the other, one before the other, simultaneously. Doesn't matter because they have no effect on each other, right? Out of these, how many of these 12 do you get heads? 6. Okay, and on how many of those have you rolled a 2 on the die? Meaning you're talking about the probability of head and die roll of 2, which is only this particular event. Okay, and therefore this is 1 out of the 12 possibilities. So the probability is 1 by 12 just from this. And of course, the formula for multiplication gives us the same result. We could say probability of A and B and use the ampersand to represent the fact that both the events are occurring together. Or we can keep it somewhat simpler and just put a comma there, right? So probability of A comma B is the same as the probability that both A and B occur, right? So it's just a different notation, and this might be more concise when we are talking about many events rather than just 2, right? So if you're talking about 5 events A, B, C, D, and E, then it's better to put a comma than to put so many ampersands. That's all.